Hi everybody, we will talk about Heine-Borel Theorem and I will follow the proof listed on the Wikipedia page, and you can find the link in the comments section below this video. The statement says that for a subset S of Rn, the following two statements are equivalent. If S is closed, S is closed and bounded, if and only if S is compact. This is the statement of the theorem. It's easy and simple to state, as you see. And for the proof of it, we will follow these steps. First, we show that if a set is compact, then it must be closed. Here, set always means that a subset of the Euclidean space of Rn. Okay, don't forget that. And if a set is compact, then it's bounded. This two together shows that B implies A, and then we will state a lemma and prove that it mainly says that a closed subset of a compact set is closed, and this implies the next part of our proof. If a set closed and bounded, we will use this lemma in the proof of this statement. If a set is closed and bounded, then it's compact, and this complete the proof because this makes A implies B. This is the main chart of our proof, and let's get started. So the first statement is that if a set is compact, then it must be closed. Here S is a subset of an Euclidean space. On the contrary, that say S is a compact set and it's not closed. Okay, then it must have an accumulation point that is not contained in the set S. And remember that an accumulation point is a point such that on every neighborhood of the accumulation point of a set, we can always find some points other than that point itself that belongs to the set, right? For instance, if we take a point at the boundary at any neighborhood of this point, say A, and the set is S, we can always find another point other than A that belongs to this set. No matter how small you take, you will always find a point within this set. Another characterization of this accumulation point, we can always find infinitely many points that belongs to this set within this neighborhood. This makes a neighborhood, and if it's closed, if a set is closed, it contains all of its accumulation points. So our assumption here is that we have a compact set and it's not closed, so it must have an accumulation point that's not contained in it, right? So we should have a point like that. So let's call this point A, and now we construct a new set of sets, say collection. We call this C prime, and this set contains n x's which are neighborhoods of points of x, and for each x we want this property. For each x, the nx, the neighborhood of x, nx, intersection vx is empty for a neighborhood of A. We also index it with x. It seems a little bit confusing, but the idea is we have a set S. We pick an accumulation point A, and it's not contained in the S. And for each point X of S, we pick a neighborhood. We call this nx, and for this neighborhood we pick another neighborhood of A, and we call this vx, and the intersection of these neighborhoods nx and vx, n sub x and v sub x, is empty, so they are disjoint. So how can we be sure that we can always construct such a set, or such a set as called C prime? So for any member of x we can find an open set around it, because this is inside of S, right? So this is the definition of the point being inside of S. And since A is an accumulation point, and actually it's a point inside the Euclidean space and dimensional Euclidean space, we can always find a neighborhood around A, and it will contains, for this we don't need that information, but it always contains some other points than itself from S. So we can make these two disjoint by making the radius of these balls, these open sets, as small as we want, as we need. So we can pick such sets and we can construct this set C prime. So this collection of n x's, right? The C prime collection contains n x's, but for every n sub x we have corresponding vx. We are not using these v sub x's, but we have this collection, and this collection covers all the s. So because for every point we have a neighborhood, right? It's a simple fact. So C prime covers whole S. It may be finite or it may be infinite. So in any case, since the set S is compact, we can find a finite subcollection of C prime that covers S. Right? This is the definition of compactness. So we may find a finite subcollection of C prime. Let's call it C double prime. And it contains the sets n1, n sub 2, n sub 3 up to n sub n. So we have finite sets inside C prime, and this covers whole set S. And for each one of them, we have a corresponding V sub 1, set V, say V sub 1, V sub 2, V sub 3, and V sub n. This is another set. These are neighborhoods of A, and n sub 1 is disjoint from V sub 1, and n sub 2 is disjoint V sub 2, and it continues like that. So we know that V sub 1 has a point that is not contained n1, V2 has a point that is not contained n2, and so on. So we can construct, since this collection is finite, let's call this V, the collection is V. Since V is finite, we may take the intersection of all of these V n's. Let's call E1, I is from 1 to n, and we can take the intersections of Vi's, and we know that this is not empty because every one of them contains A, and every one of them contains infinitely many points from A. Since we take finite intersection, this should contain at least one point from S other than A. So here we have a contradiction. Actually, we finished the proof because we claim that the union of n's and I covers S, but we see that the intersection Vi's are not contained, say disjoint, right? Is disjoint from all the unions, and I's, and this is a contradiction because this C double prime cannot cover S. So why do we have this contradiction? Because we assume that S is not compact. Sorry, S is compact and it has not closed. So it has an accumulation point that is not contained. So it cannot happen. If it's compact, it should contain all of its accumulation points. And this says that if the set S is compact, so it must be closed. And this finishes the first part of our proof. Now we will show that if a set is compact, then it must be bounded. It's rather simple from the first one than the first one. So let's say that S is a compact subset of Rn, and we can construct an open cover containing balls with radius 1 for each point of S. So we have S here, and for every point X, we just take a ball with radius 1 around it. So this bubbles cover whole set, right? So this is an open cover for S. So we may find, since it's compact, we may find a finite subcover. Let's call it again C prime, or we don't need that. So we know that we have a subcover for this collection, right? That comes from the compactness of the set S. So let's call it C prime. This is the finite subcover, and the balls, let's name them B sub 1, B sub 2, B sub 3 until B sub n. Okay, we have a finite ball, set of balls here, and now we can take the centers of these balls and the distances between 0 and these balls. So we can construct a set, or we can directly take the maximum. Let's call the R the maximum of this set, the distance between 0 and X, that is X is center of BI, where BI is a member of C prime. So what I mean here, we take every ball from this finite set and take distance from each ball center to the 0 and list all of these distances, and we take the maximum of it. Let's say we have S here, and we have balls around each point, and we may take the distances between the centers, and we take the maximum one from B to B from the 0 to center of B. And then the ball centered at 0 and the radius with 2r contains all BI's, right? And hence it contains the S also. So we can say that S is bounded because it's contained in a ball. So now we know that any compact set is closed and bounded. So any compact subset of Rn, keep in mind that any compact subset of Rn is closed and bounded. So now we have a lemma to prove for which we need in the proof of the second part. A closed subset of a compact set is compact. So we have a a closed subset of a compact set, and we want to show that this subset is compact. Let's call this closed subset is K. So let's say that K is a closed subset of a compact set T in Rn. And here we want to show that K is compact, right? So assume that we have a open cover called CK for K. Okay. The question is, can we find an open subcover CK of K? Let's call this C. The cover, assume that we have a cover C, open cover C of K. Now if we look at this set containing all the sets of C and Rn minus K, this covers the whole set T, right? So we have a closed set T here. So we have a compact set here T here, and we have a closed subset K. Okay, and we have a cover for K. And the complement of K union with complement of K is here, right? And we take union of these all the sets of C. This this will cover the whole T, right? And since T is compact, this set should have a finite subcover that covers whole T. So let's call this subcover C prime. C prime is a subcover of C union R to the n minus k, and it has finite number of sets contained in it. So if we take the difference, if we take out from C prime the Rn minus k, we still have finitely many sets contained in it, and this covers whole K, right? Because it contains all the T. We take the Rn minus K out, and this set should cover whole K. Actually, we don't need to take out the Rn minus K, right? This also should cover, but if we take the Rn minus K out, now C prime, this thing is a subcover of C. Cover of C, because at the beginning we have all C's and plus Rn minus K. So the only difference between these two sets are Rn minus K. If we take this out, this still covers the whole K, and all the sets contain this set is also a member of the cover that we take at the beginning C, right? The given cover. So at the end, we for any open cover of K, we can find a finite subcover of it, right? So this is exactly the definition of the compactness. So we can say that K is compact. And this finishes the proof of the lemma. Now we are ready to prove the second part. So let's say that S is a closed and bounded subset of Rn, and since it's closed, we can find a box, we call this T0, that contains this bounded set, right? For example, in one dimension, the box is just a closed interval. For two dimension, we just take the cross product of minus a plus minus the closed intervals. So we have a 0 here, and we have coordinates minus a, minus a, and in three dimension we have a cube centered at 0, right? And all the dimensions are 2a, etc. It goes like that, but after three dimension we cannot draw it, unfortunately. So this is a box that contains S. So we have a closed and bounded set. If we can show that S is contained, so in any case S is contained here, and we know that S is closed and bounded, and if we can show that this T0 is compact, then as being a closed subset of a compact set, S should be also compact, as we have shown on the previous lemma. So our aim is now to show that T0 is a compact set. So to show that T0 is compact, that at the beginning, let's assume that T0 is not a compact set, right? On the contrary, say it's not compact. Say that T0 is not a compact set. So what will we have if T0 is not compact? We should find an open cover, right, which does not admit any finite subcover. So for the simplicity, or to be able to draw things on paper easily, let's assume that we have in two-dimensional case, and we have T0 like that. Remember, S is contained in it and it's closed, but we are not drawing S right now. So we have T0. Our aim is just to show that T0 is compact, right? It's a box in Rn, in our case R2, and it has a open cover, and it does not admit any finite subcover, right? So I'm not drawing the cover, the bubbles, but assume that we have an open cover, and we divide the box into 4 smaller ones, right? We may always do that, but in n-dimensional case, we will divide all the intervals that we take the product, just make them half length, right? Or let's say we divide 2 to the power n smaller boxes. In our case, we have 4 regions or 4 boxes. In one-dimensional case, we divide the interval into 2 other intervals. 2 to the power 1 is 2. And in 3-dimensional case, we just have 8 smaller cubes. We divide this cube into 8 smaller ones, right? You can imagine it easily. So we will have 8 smaller cubes. So in general, we will have 2 to the power n smaller cubes. Here we divide the compact or closed. We don't know it's compact or not now. But we can always divide this cube, n-dimensional cube, into 2 to the power n smaller cubes. And now the members of the cover. Did we give any name to the cover? So say that C is cover, is an open cover of T0. So one of these smaller T's, one of them should be covered from infinitely many of C's, right? Otherwise, if all these 4 smaller cubes covered finitely many C's, then it means that T0 is covered also from finitely many elements of C, but it's not compact, so it should not admit any finite subcover. So at least one of these 4 smaller cubes must be contained in infinitely many C's. So let's call this one, at least one of them is like that. Let's call one of them as T1. Now we know that T1 is covered by infinitely many members of C. And here we can also divide T1 into 2 to the power n smaller cubes. And also one of these 4 smaller ones should covered by at least infinite many of C's, elements of C's. And let's call this one T2. And in this manner, we can construct a sequence of boxes, right? T0 is contains T1, and this contains T2, and this contains T3, and it goes like that. And here we say that we have in general we have Tk, and it goes like that. And for any k, we have the dimension or radius. Let's call it a, the radius of this box. And here the radius should be 2a divided by 2 to the power n, right? 2 to the power k. So, and as we increase k, the dimension or the radius of this box tends to go to 0, right? As k goes infinity, 2a divided by 2 to the power k goes to 0. This means that these boxes are getting smaller and smaller, right? We take this one, for example, this one. These are getting smaller and smaller. And here we can construct a sequence. Let's take a point x0 from T0. say it's here, and we can take a point from x1, t1. T1 is this box, remember. We take x1 here, and t2 is here. We can take x2, and it goes like that. So we have a sequence of sequence of points in Rn, and we let's write a couple of them. Xk, they goes like that, and the distances between these 2 points, successive points, are getting smaller and smaller because they are contained always a smaller box. So this is a Cauchy sequence, right? Cauchy sequence in Rn, and we know that any Cauchy sequence of Rn should be convergent. It is convergent. Let's see. So it has a limit point. So we know that the limit as k goes to infinity, xk does exist actually. And this limit point is contained in t0, right? Because for every k, all the xk's that comes after this one, for example, all the x's after x1 are contained t1, right? They are all contained t1, and all x's after tk are contained tk. So the limit point also should be included in t0, right? T0 contains all the members of the sequence, so the limit point also should stay inside t0. So here we should say that all t's are closed, and so they should contain their accumulation points, right? So the limit point should contain all of tk's, and eventually it should be inside t0. So we are getting closer to the end of the proof. C must have a member U that contains L, because L is contained in T0 and C is an open cover for T0, and hence it should have a member that contains L, right? And since U is open, we may find a ball centered at L that stays inside U, right? So we have L here. Let's draw it somewhere here. We have the accumulation point of so the limit point of this sequence. Let's draw it with purple here. We have the limit point L, and C should contain an open set U that contains L, and since U is open, we may find a ball centered at L around, this is the BL, centered at L. So we may find L, but we can make TKs as small as we wish, and they will eventually all around L. So we can find a TK that stays inside the ball B, right? So we may find a TK. So we may find a case such that TK is subset of BL and it's subset of U. This is a contradiction, and you may want to find it, what's the contradiction by yourself. You can pause the video and think about it. So in the construction, we assume that all TKs are covered by infinitely many C's. Let's say none of them admits a finite subcover of C, right? But here we see that this TK and all the ones that is greater than this particular one can be covered by just a single U, and this is a member of C, right? This is not possible. This is a contradiction. So why do we have a contradiction? Because we assume that T0 is not compact. So this is not correct. Actually, we may prove this without making a contradiction. This shows that after some point, a TK is contained actually just by one member of U, and the rest follows that we should have a finite subcover. But here in our construction we assume that all TKs are, none of these TKs admits a finite subcover, but here we see that on the contrary there is one that admits a finite subcover, just one actually of members of the open cover that we take at the beginning. So we conclude that T0 is compact. So we have T0 is compact, and by being a closed subset of compact set S, compact set T0, S must be also a compact set. And this finishes our proof of the second part and also the whole as a whole. So as a summary, we have shown that if a set is compact, then it must be closed, and if a set is compact, then it's bounded. This makes that B implies A, and at the end we have shown that if a set is closed and bounded, then it is compact. And to prove this, we have used this lemma: a closed subset of a compact set is closed, and together these show that if a set S is closed and bounded, then it must be compact. And this finishes the proof of the Heine-Borel theorem.